Okay, so we already handled the term A and B, and the C is a problem, but we are going to assume for now, we will assume that it is small op 1 over square root n. So even if you multiply square root n to C, it will converge to 0. So remember how you interpret this. And so 0 is, so this is term A, this is term B, and this is term C. And remember, we need this guy, square root n times this. So you may rewrite, rearrange the terms to have square root n times beta hat minus beta 0 is something inverse, something square root, something minus blah blah blah. And let's see. We know this term converges to a normal distribution. And we assume that C is small op 1 over square root n, which means even if you multiply square root n, C will converge to, so square root n times C will converge to 0. So then as a result, in the end, we have, so it is ignorable, it converges to 0. So we have this limit distribution. So, and as a result, the asymptotic distribution is G inverse omega G inverse prime. But G is symmetric, so you may not need to, you don't need to use the prime. So the asymptotic variance is defined this way. It is quite, in some sense, it is similar. It is similar because XX prime is involved. And in the OLS, we had, remember, sigma squared here, like here in omega. So there was no density, and this part was replaced by sigma squared. So pretty similar with slight modifications, and so you may understand it in a similar way, in the same way. Now the remaining is how we can prove the convergence of C, but I thought I'm not going to explain much about this. So it's complicated technique. This requires an assumption that the function G is stochastically equicontinuous. So the term is quite already, overwhelming. It's stochastic equicontinuity. Every single word is hard, is difficult to understand. So first, let me explain. We are calculating difference. This difference in the braces, the difference is sample mean and the population mean. So in some sense, you may understand this as the convergence error. So this sample mean is converging to the population mean, but in the finite sample, the convergence is not complete. So there may be still some error in the convergence. So convergence is not complete yet. So say I will call this convergence error, this difference. Also, this difference is convergence error. The difference between these two guys is that this is evaluated at theta hat and this is evaluated at theta 0. So the convergence errors are evaluated at two different points, theta hat and theta 0. And we know theta hat is converging to theta 0 in the end by the consistency assumption. So if theta hat is consistent, it will converge to theta 0, but at the same time, we are looking at the convergence error, how quickly the function, the sample mean, converges to the population mean. So this means then, in the end, it is not about the convergence, but it means that the convergence rate must be similar at two different points, which are close to each other. So there are 2 points, theta hat and theta 0. They are close to each other, and what we are looking at here, what we need here is the convergence error at one point and the convergence error at another point must be similar. So their difference should be converging to 0 quickly enough. Quickly enough, how quickly? It must be faster than square root n. Even if you multiply square root n, still the difference must be 0, converging to 0. So then, why is it called stochastic equicontinuity? So it is, in some sense, it is continuity because, well, like as theta hat converges to theta 0, g, the convergence error is converging to the convergence error at theta 0. So the difference convergence rate must be continuous must be continuous around theta 0, and it is called equicontinuity because it has to be satisfied for any kind of theta, like any theta and g. So we assume that a function is stochastically equicontinuous. It's hard to say. So it means that the convergence is equally going to 0. Similar at the rate is convergence rate is similar across different points, continuous and similar. So that is summarized into equicontinuity, and it is stochastic. So it is continuity, but it is stochastic. It is random variable. So we have to call this stochastic continuity. Of course, this converges in probability. I just simply ignore the subscript because it's obvious, but I'm sure that some of you may be confused. In case if you think you are curious while you are confused, ask me questions. Anyhow, this is all I can say. And then how can we show the stochastic equicontinuous? How can we show that a function is stochastically equicontinuous? It's the true proof is one course, one semester. And even when I took a course at Yale I took this course from the statistics department. David Pollard, Professor Pollard was one of the inventor of this theory, and he said he cannot understand some parts of this proof. So I gave up. So I do not know. But just if you want to apply this theory, you may use this paper. In this paper, there are sufficient conditions are given for this condition. So Don Andrews, he is also a professor at Yale. He lists several different kinds of functions which satisfies the stochastic continuity. So most of the functions you use in your dissertation would be one of them. Like for example, if your function is say bounded and with finite parameters, then it's stochastically continuous. It may not be true, but something like that. It simplifies the assumptions. So you may use if you need to use the theory, I recommend this paper. And then what does it mean? Its implication is if a function is stochastically equicontinuous, it means that this uniformly converges to this. And my explanation was pretty obvious. So the convergence rate is similar in a closed point. But however, uniform convergence is just one result. So it is only sufficient for uniform convergence. It is actually, so this is stronger than uniform convergence because it has to be 0 even if you multiply square root of n. So even if you multiply a large number, still the difference must be negligible. So it's a stronger assumption that uniform convergence. And alternatively, you may, exactly this is uniform convergence. You may remember we used it earlier. Uniform uniform low large numbers. And this is the definition. This is the definition of stochastic continuous. So it's very confusing and I think I'm confused. Anyhow, in this example, C satisfies this condition. So I cannot prove that, and in most cases, it is important. And I see these techniques many times. Then you may apply this. Okay, I will go to the next topic in the next video. So thank you for watching, and I will continue later. Bye.